I first want to welcome all the family members who are visiting us this weekend. I hope you have a lovely time with your students. Tonight, it's my pleasure to welcome Dr. Cynthia Keppel, an Annapolis alum, to St. John's College. Dr. Keppel is the head of the Physics Division at the Department of Energy, Thomas Jefferson National Accelerator Facility, commonly known as Jefferson Lab. Her career is quite remarkable. She has delved into pure research, focusing on the quark-gluon structure of the nucleon, as well as applied research, bringing what she has learned in her research to the medical field with much success. She holds several patents in the field of medical technology, one of which received the Medical Device Breakthrough Award in 2018. She is a founding member of the Hampton University Proton Therapy Institute, which uses proton radiation for cancer treatment, and she has served on several national boards, including the National Nuclear Science Advisory Committee and the National Institutes of Health National Advisory Research Resources Council. In addition to her work in the lab and in medicine, Dr. Keppel has mentored high school teachers and worked to support underrepresented minorities in the field of physics. Please join me in welcoming Dr. Keppel to St. John's.
So it's a welcoming back. I'm quite thrilled to be here. Thank you all for showing up on a Friday night. I'm going to try, this is a talk I haven't given before, so you guys are all guinea pigs, and we'll see how this goes. We're going to try to move all the way from Democritus, thinking about the very first atoms, all the way through nuclear physics and into medical applications of nuclear physics. So we're going to be a cheetah here. That's what I have. We're going to go a little quickly and lightly through all of this. But I have a method to my madness and why I want to do that. So let me try to roll with that. I'm very, as I said, happy to be here. I'm an alumni of the class of 1984, and I love St. John's. I actually found few of my life's loves here, my husband, and also physics. And Isaac Newton. So many things to fall in love with. And I actually did my senior essay on the general scholium to Newton's Principia. So I was physics focused a little bit then. Although I really thought I was going to be a race car driver. I did that for a little while. So there's a lot of cool things in the universe. So anyway, with no more ado, I thought I would talk about, like I said, I'm going to roll through these things, and my real reason for putting up these slides is I like to point out that one of the things St. John's can give you is this ability to do many things. You're equipped for not one career path, but maybe many. And then also I really like these funky combined animals, and I couldn't resist using them in something. So I think of myself as a funky combined animal of some kind. What is one part of this animal? One part of this animal is really fundamental nuclear science, and I'm going to focus on that to start with. And what you're looking at here is this beautiful graphic from the National Geographic, which takes us from the birth to the death of the universe. And nuclear science is in this one little part of this whole big train. And in this part, it's very interesting. All of everything. This microphone, me, you, the room, the building, the campus, the country, the world, the stars, the planets, everything was in a little golf ball-sized ball in the first microseconds of the Big Bang. All of it was a little ball of what we call quarks, and that was it. And all of that could not exist in a little ball for very long, and so in the next sub-nanosecond, it came and cooled off. And as it's expanding and cooling off, the first things it did was these quarks became nuclei. Actually, they became protons and neutrons and then became nuclei. And so really understanding that is at the fundamental part of the nuclear science that we do at Jefferson Lab. And it's not to understand the Big Bang, it's actually to understand the forces involved and what holds matter together, what sticks everything together, what's causing mass, what's causing nuclei. And these are questions that we don't know the answer to. I had a really fun dinner tonight, actually with several tutors, and I was able, and this is an aside, I didn't plan for the talk, but just to hopefully fascinate you with nuclear physics for a brief second, I pointed out that we have fundamental quarks and gluons, and that's a fundamental theory. Right? And then we have nuclear physics, which is probably what you think of, which is bombs and reactors and MRI machines and things like that, radioactivity. Actually, we do not have a fundamental science for this at all. These are all effective equations, effective theories. The fundamental physics is sitting in the quarks and gluons. We don't understand nuclear physics, how these protons and neutrons come from the fundamental forces. So that's what we're trying to do at Jefferson Lab. And it turns out that that's what was happening here at the Big Bang. So that's what we're seeking to do. And I have a little movie that we recently made. However, as you probably noticed, we started about a minute late because we had a technology problem. So I'm going to play the movie, which has nice narration, but the sound doesn't work. But I do want to play it nonetheless because I want you to have the visual. And I'm only going to play it for 3 or 4 minutes and I'll stop it. But I'll talk you through the visual a little bit because I think it is informative and it will help our conversation after that. So let me cue up this movie. Give me 1 second. Maybe you can hear it. Nah, you guys can't hear that very well. Okay, so here we have Democritus coming in with the very first atomos, where the idea was actually amazing for the time that everything was made of atoms and a void or a vacuum, which turns out to be a great guess, but they're not different because of structure, because of the geometric structure. So we have J.J. Thomson, so you guys have studied this, where we have different models for what the nucleus looks like, and then Rutherford comes in with something like this planet-like orbital structure, which is the picture most people sit with the atom. However, we know actually Heisenberg uncertainty is always at work, and in fact the electrons don't orbit. There's a kind of a probability cloud distribution in the atom of electrons, and at the very, very center there's a nucleus. And it's tiny. And to give you a feeling how tiny that is, we're zooming in. So if the Earth is 10,000 meters across, roughly, we're going now to MIT. My colleagues worked with us at MIT. They have a nice visualization lab to make this. So we're going to the campus, which is 3 orders of magnitude down. And then we're putting on top of the MIT dome this swimming pool, which is about 1 meter in diameter. And we're going in 3 more orders of magnitude to a millimeter-sized cube, and then a micron. So that's 3 more orders of magnitude down, and then going down to a nanometer. So that's a billionth of a meter, and you see the little oxygen atoms rotating around. That's actually what causes food to cook in a microwave. And then we go down to an angstrom size and continue in until we get finally to the proton inside the nucleus. And now we're at a very much smaller distance scale, about 10 to the minus 15th meters. And inside of there, you see this boiling mass of stuff. And this is the quarks and gluons. And this radius is, as I said, it's 1 femtometer, so 10 to the minus 15th meters here. And there's protons, and there are also neutrons, which will appear. The narrator on the video is talking more slowly than me somehow, so I'll wait a moment. But the reason that this is shown as dynamic is that the quarks and gluons are constantly exchanging energy between them. So much so, in fact, oh, I understand what's happening. They were talking about shutter speed. So this was a camera of the proton. You change the shutter speed and you see different things. At 1 shutter speed, you see the fundamental gluon interactions. I'll talk about what that is, but it binds the quarks together. And at another shutter speed, you see these 3 guys, and they define the quantum mechanical properties of the proton, just those 3 quarks, even though there's billions of them in there. That's a bit of a mystery, too, how that happens. And the neutron is the same, except it decays. It's a little more massive, and so it's has some extra energy that it can decay off. And I think I'll stop this here because that's already got enough to think about. Okay, so that was a whole bunch of, oops, hold on. Yeah, we're there. Okay, great. So that was a whole bunch to think about. So I thought we'd pause for a moment and just talk about those amazing thoughts that are in there. So just a few. There are many amazing thoughts in there. So first, the realm of the building blocks is really small, right? Really, really small. And so you got that, but I'll give you another way I like to talk about that. If we took this auditorium and we filled it with grains of sand, right, little grains of sand, and then we built a bunch of auditoriums and we ringed the world with them. And we filled every auditorium with grains of sand, all the way around that 10,000 meter radius world, right? And we did that. And we counted every grain of sand. You'd have as many atoms as are in one of you. So that's how much smaller they are than grains of sand. So first amazing fact is that things are really, the fundamental building blocks are really small. Okay, so that's difficult to do experiments with, trust me. But we can do it. All right, so the next thing is that most of matter is empty space. So what do I mean by that? So you saw that picture of the nucleus. So now this auditorium is no longer filled with sand. Instead, it's empty space. And there's an electron winging around the outside. And so what would the nucleus look like in that picture if this was an atom? Or there's a bunch of electrons swinging around the outside. The nucleus would be something like a little dust speck at the center. And yet, all of the mass of the atom, and therefore all the mass of you and me and the microphone, is sitting in that little dust speck, right? Because the nucleus carries all the mass. Electrons are essentially massless. So most of matter is completely empty. So that's interesting. Why can't you put your hand through the table then, right? Empty space through empty space. Why can't I do that? Well, there are forces involved, right? And so now we talked about that electron winging around the outside, and so you've probably looked at those orbital kinds of pictures of atoms many times, and you're like, but not really thought through either that it's a drawing, so you can't get that little dust speck compared to the outside, but it's all, so you can't get the empty, but the magnitude of the force, all that empty space, you can't put your hand through it. What's going on there? So I can tell you that, roughly speaking, the force that binds those little quarks inside the nucleus in any one of those nuclei is about the same as if you took two giant 18-wheeler trucks and the energy of a collision at about 70 miles an hour, I like vehicles, sorry, of those two trucks slamming into each other, that amount of energy is about what's happening in every interaction inside of there. So you've got lots of these little guys in you, and you have lots of that level interactions happening inside you all the time, constantly. It's what creates matter. So that's all fascinating. And then we also have action at a distance, which is in that little video. Now, why do I say that? Well, it's the same thing we said a little bit ago. How you all accepted that the nucleus is sitting as a dust speck and the electrons are winging around the outside. How do the electrons, which are negative, the nucleus is positive overall, how do they know it's there? They know it's there, and they know what charge it has. Are they talking? How do they know? But they know, right? And not only that, it's the same orbital force that causes, it's the same orbital kind of mechanics, I should say, different force, that causes the moon to orbit the Earth, right? The moon's orbiting the Earth due to the force of gravity. The electrons are orbiting the proton due to the electromagnetic force between the charges. So how does one charge know, right? I have a positive charge here and a negative charge here, and you guys would say, opposites attract, likes repel, these would come together. But so they don't only know they're there, they know what charge the other one has. So that's interesting, right? We have action at a distance. And so just to give you a feeling, I think physics is really magical, so I thought I would give you just take yourself back in time and we'll try to experience some magic. This is an experiment that you don't do here. You do some amazing landmark experiments here, but this is Hertz's first experiments in trying to understand this action at a distance. And what he did in the 1880s, so 1880s, right? In the US, we're having the gunfight at the OK Corral. The Ottoman Empire is in extant, right? That's what's going on. And in Germany, this guy's doing this. He's curious about this, and he creates this thing where he has one electrode, so these two balls, so you see them here and here, and he puts a high voltage between them. And you've probably seen pictures of things like this. Don't try this at home, but you'll get a lightning kind of arc between the two balls, right? So he can do that, and he can make he can use high voltage to do that. Very clear how that happens. And then he takes this thing, which just is an antenna loop. It's not attached to anything at all, and puts it at the back of the lecture hall at University of Heidelberg. And he powers up and creates lightning here, and lightning occurs over there. So think how people felt then, right? This is bizarre magic action at a distance. How are you doing that? But it was actually a demonstration that the electromagnetic field is everywhere. I created here with the high voltage, but it is in fact tapping into an energy that permeates all of nature. And a perturbation of it here caused a perturbation over there. And that's what's happening inside the nucleus. That's what's holding all these things together, and that's why you can't put your hand through the table. So what he was trying to do, what inspired him to think about, is there really action at a distance? Does this electricity really extend over the whole of nature? He was trying to look into this work that James Clerk Maxwell had done, unifying electromagnetism. And he thought, this really should mean that this field is everywhere. And so, did you have a question?
Oh, no, an idea that also will help us discuss the nature of light.
It actually, I will talk about that momentarily. It is, in fact, very intricately linked to the nature of light. You're correct. So, but it also is linked to our modern world. Now we send, for example, radio waves everywhere, right? We're all using our cell phones. That's how we're talking to each other. It's that electromagnetic interaction that's going on. We're sending electromagnetic fields around, Wi-Fi, how we talk to satellites in space, how we can beam even pictures with a different bandwidth approach. But at any rate, we utilize this. So another thing to take away here is that really fundamental things, trying to just ask questions and understand phenomena, actually can have big practical applications. And so I will talk at the end of my talk about some practical applications of nuclear science. So you are correct. Since you said it, I'll just say that that electromagnetic field that permeates all of space is a field of photons. It's a field of light. For electromagnetism, for gravity, it's a field of gravitons. And for the other nuclear forces that bond, for instance, the quarks within the nucleus, it is a field of gluons. Different from other things, the gluons interact with each other. But at any rate, so how do I know all this, right? I am standing here telling you guys some pretty weird stuff, right? And you're just going, she's got a PhD, she's got to be right, right? I've seen some of that on TV, I think it's right? So, but how do we know this, right? How do we do this, really? And so you can ask your question, how do we see anything, really? What happens? So here's what happens, is light comes down from some light source, this bright light here, or the sunshine, and it hits an object. It's my table again. And the photons, the particles of light, bounce into my eyeball. And my eyeball is a super sensitive photon detector, and it can tell me things like the number of photons, which my brain translates as intensity. Lots of photons, it's bright. Not so many photons, it's dark. I can look at I can process the wavelength of the photons, which my brain translates as color. All of these things, this is what happens. So we believe we see something, not because we interact with the thing, right? But because we interact with the photons, right? That electromagnetic reaction, the sea of photons is all around us. So that's what's going on. But now we actually want to see an interesting object that's really, 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 really small. Really, really, really small, much smaller than a grain of sand, right? So now the photons aren't going to work. We can't see these subnuclear structures. So what are we going to do? Well, how can we probe the realm of the ultra tiny? So we want to get down, to 100 millionth of an atom, and we're going to try to do that. So how do we do that? How do we get to that 10 to the minus 15th scale? Well, what do we want? What is the tool that we need? It turns out, you guys have studied Heisenberg uncertainty, or you will, but one thing to take away is what it tells you is that to go to the ultra small, you need to go to the ultra high energy, right? So delta E, delta X, or delta P, delta X, momentum times distance is a constant, so high momentum, small distance, large distance, low momentum. So, all right, so we need high energy to have a probe. So that's why our photons aren't going to work. We have to have something point-like, because if I want to understand the nucleus, I can't send something in that's going to blow it apart. I have to be able to go into it and probe it. So I need something smaller than a nucleus, and I need something that's going to interact with the nucleus in a way that I understand. So under electromagnetism, we don't completely understand, but we 95% understand it. That's a bold physics statement right there. But we think we understand it anyway. So those are the three components that we need to really probe down inside the nucleus. So basically, we need high energy electrons. They interact electromagnetically. They're negatively charged. If we can accelerate them to a high energy, we can get to the little tiny, tiny distance scales that we need to, and they are, in fact, point-like. So there we go. We're going to use high-energy electrons from a particle accelerator. This is the Thomas Jefferson National Accelerator Facility. It's a little hard to see in this picture. It's actually, most of the action is underground. There are 2 electron linacs that send electrons around a particle accelerator track of about 2.5 miles. And then the electrons can interact with nuclei in different experimental halls and bounce out. Now we can't use our eyeballs. We don't want high-energy electrons going into our eyeballs, and we don't want to stand in these experimental halls when they're running. There's radiation area. So we detect them in giant particle detectors that we make and create. So this is what my team, experimental physicists, do a lot of, is work on new particle detectors and new targets, to be honest, because while nuclei are in everything, we may want a polarized target or some kind of odd nucleus or something to understand what's going on. So it's just like looking at anything, except it's not visible light, it's high-energy electrons. Our target is teeny tiny, and they scatter out into man-made giant eyeballs into nature that then send data to computers and ultimately still have to go to a human brain. So that's how we see the ultra tiny, and I can't help but show baby pictures because this is home and the lab that I lead and love. So this is again the Jefferson lab, and you can see the structure more or less, the 2 long linear accelerators here. They send the electrons around a race course, accelerate, race course, like that, and then eventually wing it into the experimental halls. The experimental halls look like this. This is hall B. This is one of the detectors. I don't know if you can see, there's a kind of a human down here in the picture. Hall C may be easier to see. You can see some of the structure here, like stairways and ladders, to get a feeling. So these giant eyeballs into nature our experimental halls are the size of this auditorium, except a little taller, basically, to try to do these experiments. So these experiments are extremely difficult. And so I thought about difficult experiments. I was here a few weeks ago for my homecoming, and we were wandering, looking through this building, very happy about the nice state of the building, and we wandered into a lab room, and I saw a Millikan oil drop experiment and a Wimhurst machine and things that I remember, and these are beautiful experiments, right? They're brilliantly devised. And you guys have probably experienced that they're very difficult to get right, yeah? And they're very hard to get the charge to mass ratio of an electron correct. So imagine what we do, right? This is what we do. These are our giant eyeballs. These are modern particle physics experiments. These happen to be at Jefferson Lab. There are some other particle accelerators in the world, not a lot, but there are some. And we're working hard to make this stuff work. Unlike a lab experiment that you do for class where you know what answer you should be getting, we don't know what answer we should be getting. So that makes it even extra hard, right? We have to calibrate and try to reproduce things we've seen before and bootstrap. Very challenging stuff, but very fun. So the very fun aspect is what I wanted to tell you is if you want to come work with us, do it. Come, please. We have lots of opportunities. It's U.S. Department of Energy. One of our missions is to train the next generation of scientists and to provide science to the public because ultimately the public is who funds us to do this stuff. So we just unfortunately closed the DOE SULI, but this comes up every fall and it funds students to come and be at Jefferson Lab and other national laboratories, all 11 laboratories in the Department of Energy system. Not all of them do particle or nuclear physics, but all 11 research laboratories have SULI students. And then this one is specifically specific to us, and it's aimed at how to accelerate particles. And I hear from one of your faculty members that you all also have funded research programs that the college funds. So if you had access to one of those, you can reach out to me and just basically we can set you up with a research experience. Every summer we have between 200 and 300 students who come and do work and research at the laboratory. So you won't be alone and you'll have lectures and other students and hopefully get a feeling for what it's like to do this kind of work. This was my SULI student 2 years ago. SULI is Science Undergraduate Laboratory Internship, sorry. So anyway, that's my little advertisement. And so I thought I would segue. Why does the taxpayer pay for this? Well, part of it really is an investment in human curiosity, answering these questions that we do not know the answer to, right? What is the origin of nuclear physics? And if we learn that, you know, a feeling that the U.S. will stay ahead maybe is matters to our government, but also just a feeling that humanity will take that information and do great things as we have historically. But one of the things that happens are spin-off technologies all along the way, because to do this kind of very difficult experiment, we have to think of new ways to do it, which means we develop technology all the time. So I thought I particularly am interested in cancer care, and so I'll talk to you a little bit about some medical technologies that we've worked in that realm, and then one that's not, but that's kind of fun. So this is some of the first work we did. This is gamma detectors for, whoops, oh no. Oh, for functional breast imaging, so I'll explain what that all is. So these are the workhorse detectors of nuclear science. They're scintillators and photomultiplier tubes, and what we use those for is when a particle comes in, like one of those scattered particles, we're creating our giant eyeball, when it comes into a scintillating material, it excites the atoms that material is made of, and as the particle traverses along its way, those excited atoms now go back down to their ground state. When they do that, they emit radiation. That's called scintillation. It's scintillation light. And if the particle had a lot of energy, they emit a lot of light. If the particle had a little energy, they emit a little light. And so by putting scintillators in the path of the beam, we know two things. One, that a particle came through here, and the other is how much energy it had. So the scintillators are a workhorse for particle physics. And of course, now we need to send that light using the photoelectric effect. We use photomultiplier tubes, which convert that light into an electronic signal, which we then digitize and then send along to our computers, and our brains look at it and think about it. So that whole process is over here. How does that have to do with breast imaging? Well, standard breast imaging, like a mammogram, is actually a digital X-ray. And so here, for instance, is a mammogram that's showing, and so now how does an X-ray work? An X-ray works what we call structurally. So what happens is as the X-rays go through, like you get a dental X-ray, the X-rays come through, your teeth are more dense than the soft tissue around your mouth, and so they absorb more X-rays, and so they cast a shadow on a screen on the other side, or on a detector that goes to a computer on the other side. So that's the structure, right? It's looking at the density. Density is structure. So that's what a mammogram is. It relies on the fact that the tumor is a little denser than soft tissue around it, and maybe causes something called microcalcifications, which are also a little bit denser. So you're looking at something like this, but this is a difficult mammogram to read. There's a lot of dense breast tissue in here, and maybe it's a little denser here, but maybe not. It's hard to tell, and there's a couple microcalcifications here and here. It's very hard to tell what's going on. So what you would like is a functional image. So a functional image is a very different thing. A functional image doesn't talk to you about the density or the structure. It talks to you about what's going on biologically, what is the cell function. So what we can do is inject patients with a radio-labeled substance that preferentially goes to the tumor. So that sounds like magic, but it's not. A standard radio tracer substance like this is called fluorodeoxyglucose. So key in on the glucose. Tumors are aggressive, right? They're killing things around them, and they're reproducing, and they're growing, and they're doing all kinds of stuff. So they tend to be more active than the tissue around them, which means they need more sugar. So they'll take up more glucose than the tissue around them. If we can radio label that glucose, right, now it's going to the tumor just because the tumor's picking it up, but the radioactivity goes out of the body. And so now we can detect it with nuclear science detectors. So this is where this technology comes in. So we can detect that, and what does it tell you? It tells you the function. It tells you those cells are eating a lot of sugar. So that's what you're looking at here. Right? So while it's not so clear on this picture exactly where that tumor is, it's pretty darn clear here that there's a lot of functional activity right there. And then we can actually overlay them so that you can get structural and functional information. So we patented some of this, and a startup company moved it forward, and then another company bought it, and now it's called molecular breast imaging because it's now in the corporate realm, and they make it sound better and look better than we do. But at any rate, it's used for people with dense breast tissue. Mammograms are still a great screening tool. It's inexpensive, and you don't have to inject anyone with a radioactive substance. However, for dense breast tissue like this, there's now a national recommendation to do MBI. So it's a complex it's a problem-solving tool for complex mammography. So that's one example. This is a pretty cool example. A big challenge is what to do for people with an aging population, and people with Alzheimer's and Parkinson's, and even traumatic brain injuries. And so people are trying to develop various drugs to help with that. And so you don't just test on people, right? We begin early on testing on animals. If something looks promising, cells in a petri dish, if you will, first, but moving on to animals. But the animals you want to do that kind of functional imaging to watch what's happening in the brain, right? Is this brain changing its function or not? But here's the rub. The animals won't stay still in the imaging devices, right? Unlike a human who you can tell, please stay still, you're in an MRI or a CT scan or whatever you're using, the animals don't stay still in the scanning device. And so in this case, we're using positron emission tomography, which is FDG, emits positrons. That's the radiation it emits. Tomography means three-dimensional imaging. So we're trying to image these little rat brains, mouse brains, actually, sorry. And the question was this. The studies were done for what looked maybe to be like potential new drugs, but the animals were anesthetized to watch the function because they can't move around in the device, or we can't get good resolution. What if that animal, when awake, actually functions differently, and perhaps that potential new exciting drug isn't as exciting or is even more exciting in an awake animal? So the challenge was, can you do awake animal imaging? So that's what we were able to do here, is to actually track the little guy. So he's awake, he's in a ball, and he's got these little mirrors on his head. So this is kind of like GPS triangulation to monitor where he is, and he's not running around the lab. He's in a ball on the table, but he's awake. And then the radiation comes out into our same cameras, measuring the gamma radiation using these nuclear physics detectors. And what you should take away from this is that this is just a structural image. This is a three-dimensional X-ray, and this is if he's moving. and you see it's pretty blurry. And then this is asleep versus awake, and you can't tell the difference. So actually, this was published in Nature, and the conclusion was that actually you get a different result. So very, very important for preclinical studies of various issues, but in particular, that was Alzheimer's research we were working with. So my fave that I'll kind of close with talking about for a bit, I actually don't see a clock, so just go like this at me, but I won't talk too much longer, is proton therapy. So cancer has been with us a long time. Obviously, you all are classic scholars. You know that cancer is for the crab that we see in the sky and in the zodiac. But did you know that it's actually the reason that we call the disease cancer is because of breast cancer? This is a ductal carcinoma in situ. So you see the tumor and you see it going up the ducts here, kind of looking like a little crab with the things. So we have been after this issue for thousands of years. And we're doing better. We really, really, really are. That's good news. So how cancer is treated, the 5-year, whoops, sorry, I did it again. The 5-year survival for all kind of cancer patients in the West is about 69%. And there are many, many different kinds of therapies, but the 3 that are used the most are surgery and chemotherapy and radiation therapy. Chemotherapy is for systemic disease, so it basically poisons the whole body, including the tumor. The hope is that the case is that the body repairs faster and better than the tumor, and so one can kill the tumor off in a kind of a fractionated schedule over time. The other 2, surgery and radiation therapy, are used for local disease, so not systemic. So when we're targeting a particular tumor area, a particular tumor volume, we know where it is. And if we can get at it surgically, that's great. If we can get at it with a radiation beam, that's great. These don't need to be used. Any one of these can be used in conjunction with the others, and that is very commonly the case. So it's not one or the other. But this just sets the stage for cancer care, very, very, very broad brush in the U.S. About half of all U.S. patients, and the same is true for Europe, receive radiation therapy. And of that, almost all of it is an external beam, which means that the patient is there and a radiation beam is aimed at them. So whereas at Jefferson Lab, we have that 2.5-mile long accelerator aiming electron beams at nuclear targets to try to understand the fundamental structure of nucleons and nuclei. Here, what we're doing is we're aiming beams actually at cancer to kill it. But the technology is essentially the same. The most common kind of external radiation beam therapy is X-rays. So this is just kind of a fun shot that got a little hard to see. It should have been showing one after the other, but that's okay. This is the first X-rays device, and this is Mrs. Rontgen's hand. So Rontgen, the physicist, generated X-rays and actually imaged her ring, you can see there. And this is a modern X-ray device, beautiful resolution and imagery to see into the hand. This is for treating, this is a radiation therapy device, and what you see here is a little electron accelerator. This is exactly like Jefferson Lab, but only a couple feet long. It's sitting up inside of there, but it is exactly the same technology. The electron beam is then turned and put into a target so that it creates the X-rays that come down to treat the cancer. But that is most all radiation therapy. External beam radiation therapy is done that way. But proton therapy is new and exciting and coming out of nuclear physics, and it is the most effective external beam method. So I can stand up here and happily say that, not because I'm a pioneer, but because it's fundamental physics. So I shall explain to you why it is fundamental physics and why it is better. What do you want to do? You want to kill the tumor, and you want to not damage the rest of the patient, right? No normal tissue injury. So we want to radiate the tumor and kill it, but not radiate normal tissue if we can avoid it. So now you guys get a physics lesson. So let's see. We can walk through it, though. Have faith. You can do this. So this is Professor Bragg, who discovered the Bragg peak in 1904. He was looking at different kinds of particles going through matter, and he discovered that different kinds of particles travel through matter differently. We now understand that a little bit better because protons and neutrons are composed of quarks, and electrons are their own kind of particle, and then photons, X-rays are photons, they're force-carrying particles of light. They're this electromagnetic field we live in, so they're all very different. So if you put that in a medical setting, look at this plot. This depth in tissue here is zero depth in tissue. This is at the skin. And we're going to travel through the body, going about 30 centimeters into our patient. And this hypothetical patient has a tumor here, right? And so the conventional X-ray beam for radiation therapy will come in here and go out. So X-rays do exactly what you know that they do, right? Like we go back to the dentist and the dental X-ray. The X-ray goes all the way through the body, which is great for imaging, right? Because I want to put my film or my detector here and see where the shadow is cast. But it's not great if you want to kill something part of the way, because you don't want to deliver a killing dose all the way through, right? So X-rays are good but not perfect, and there's side effects associated with conventional radiation therapy. So let's look at the X-rays, at the protons. So the protons, they're relatively, compared to a photon, which is massless and point-like, protons are huge, right? They're 10 to the minus 15 centimeters. They're like a dust speck at the center. They're giant, right, compared to a photon. But they're also massive and charged, so they really do interact differently. So they come into the patient and don't interact much to start with. However, their rate of interaction is inverse to the square of their energy. So when they do finally interact, the probability of interaction, I guess, is a way to think about that. When they do finally interact, they lose a little bit of energy in the interaction, which means the probability to interact goes up. So they interact a little more. Well, now the probability just went up more by the square. So what happens is an avalanche effect depositing the energy, depositing the dose in that one place, which is exactly what you want for cancer care, right? You want to put all that dose in the tumor, and then they don't continue on. It sits there. So it is, in principle, the ideal beam. And you could say, well, what if the tumor wasn't right there? What if you had a situation like you do here? Photons almost always deposit most of their energy about 4 centimeters down. So what we do is do a crisscross. We do a low dose here and a low dose here and a low dose here and a low dose here, such that you get a high dose here. But you've bathed the body in some radiation. So for protons, actually what we can do is tune the energy. So because the amount of dose deposited depends on the inverse of the energy squared, you're looking at different energy protons. So that little avalanche is here, or that avalanche is here, depending on what energy beam I chose. So by creating a proton beam and tuning the energy, I can put the dose anywhere where the tumor is. And because protons are charged, I can drive them with electromagnets. And so now I have what I want. I can create what we call an optimal 3D distribution. So the tumor may have an odd three-dimensional shape, and so I need to be able to put the dose into that tumor in some shape. So I have to control in 3 dimensions. So I can drive my beam with an electromagnet because protons are charged, so I can go this way, up or down, or right or left. And I can control the depth by controlling the energy. So I can make any 3-dimensional shape that's needed for the tumor. So this shows you kind of the difference. It's very, sadly, hard to see on this screen, but I'll try to walk you through it. IMRT, is intensity modulated radiation therapy. This is photons. And so you're looking at a breast cancer patient, and the photons coming through, doing what they always do, going out the back. So this is a CT, a computed tomography X-ray. So it's a 3-dimensional X-ray cut through the chest of a patient, and the radiation dose coming through. This is a calculation. This is what physicists do in a clinic. A calculation showing different dose lines coming through. You'll see some dose going out the back, and the important thing for reducing side effects is the heart dose. So there's about 10 gray here. This is the comparable proton beam, and you don't see any of these because they're not there. They're actually stopping kind of like right along here, and the protons are stopped. And so the mean heart dose is less than a gray. A gray is a unit that we measure radiation with. This is possibly the most I would say important. This was the landmark tumor, if you will, for really moving proton therapy out into the general public in the last 20 years. So it's been a long haul. But what you're looking at now on the right side are X-rays, and on the left side are protons. And this is a medulloblastoma. It's the most common malignant brain tumor in children, and it spreads through the central nervous system. And so these two children need to be irradiated through the entire neuraxis, so their spinal cord, their brain, all the way through. And so you can imagine with X-rays, this radiation, it's dosing the entire body. And so there's a fair amount of potential side effects, particularly because they're children. They have many more undifferentiated stem cells, so they have more cells that are probable to become another, that have a higher probability to become another tumor now or later in life, as well as the direct radiation damage. Here is the comparable, beautiful proton just going right along the spinal cord. Just like that. A lot of work to deliver this and figure out getting this treatment exactly so, but very nice. And then similarly, cutting through the brain, you can see the cochlea here. One can drive around the cochlea, and this prevents the possibility of deafness or some hearing loss associated with the radiation. So hopefully you're convinced that proton therapy is a grand and glorious application of nuclear science, and so have others. When we built Hampton Proton, we were the third, and it's still the largest. But now there are many, many, many more. There are 47 in the world, and a little over half of those are in the US. So it's just been a little over 20 years, actually. So many patients now treated with particle therapy worldwide. About 20,000 patients are now being treated annually. Many clinical studies and publications. The market is growing, which means that hospitals will buy this and more will roll out. So that's a great thing. That's what you want. And many different tumor sites, because it's an external radiation beam. There's nothing to prevent treating anywhere within the body. So, and this is just to give you a feeling why, there's a few reasons why this didn't happen before. Professor Bragg worked in 1904. Why were we using X-rays? Well, it turns out that particle acceleration, I showed you what we have to do at Jefferson Lab. This is what we have to do at HEPCI. There's a particle accelerator that runs around the back beamline here and feeds these different gantry systems where the patients are treated. And these gantries that's a gantry compared to a school bus, to give you a feeling. Right? This is applied nuclear physics. The new centers, the new proton centers are smaller. This is one of the two largest centers in the world still, and it's in part designed as a research institute. The new centers are smaller, but they're smaller, right? Not small. So, but they're one room, for instance, so one room gantries, and the gantries have gotten smaller in time, good technology development as it's rolling out. But just to give you, a feeling for what's involved. Also, we needed advanced imaging, because it's only good to have a high precise tool to treat the tumor if you know where the tumor is and what shape it has. So we also needed advanced diagnostic imaging to come forward. So utilizing the Bragg peak had to wait in time. So I think I'll just kind of wind down now and tell you guys that you're really gaining critical skills that will transport you. I talked about my both our journey in asking the question from Democritus, what's everything made of? Something kids ask. What are the building blocks? What's the smallest possible thing? I keep making things smaller. What are those? So we go from this very first idea of atoms to actually seeing them, right, with high energy beams, to utilizing the technology as we move along for instance, for medical applications. So that's kind of the talk went through that path, and my life goes through that path because I'm a Johnny. So I wanted to tell you all that not just in this path, but many others, you absolutely have critical skills that will transport you, and even in high-end science, but in banking and law and anything, right? Anything that you have a passion for, you're not afraid to ask and tackle big questions. And you can converse cleanly and logically, and logically. And you've learned, hopefully, in your seminars to listen to the wisdom of others. And listening is a huge skill, so I think I put it twice. It's going to come up again. But anyway, have the ability to link disparate ideas, right? Like we're looking at protons and we can make particle beams. Hey, we could cure cancer, right? That's a disparate idea. So that kind of, that leap think. And then you can separate what is assumption, what is logic, and what is extrapolation to really see through a clear path. and dialogue effectively with others. And this is both to listen, but also to present from their perspective as best you can. So to tune your language. And you've learned to keep curiosity alive. So all of these are I thank St. John's for all these skills, and I tell you all these will serve you really, really well in life. And the last skill that I will tout is not running over time. So I'll stop. Stop. Don't know what to do. Scientists don't do this. Thank you all. Thank you. And I can't wait to chat with you. Bring lots of big questions.